Okay, so it's 4:30. We're going to get started with this problem, which is on page 213 in your notes. So if you go to page 213, it is this graph, these graphs, and graph 1 is something familiar as y equals x squared. All the other graphs, 2, 3, 4, 5, 6, are shifts and moving arounds of this graph and flips. We did most of them last class. So you should be able to take what we did last class and apply them to get the formula for each of these curves using what we did. So I'm going to give you like 2 minutes to do that, or a minute. I guess it looks like most people are in. But before that, I just wanted to make sure you guys were aware of the stuff that was posted about the midterm. So I'm going to go to that now. So midterm reminders and practice midterm posted. Basically, everything you need to know is in this folder called midterm 1 info. So make sure you check it out. I've said a lot about it before. But the new thing is that there is a practice midterm. And you should definitely check out the practice midterm before the midterm because it's the same like format. So it's going to be the same number of pages, same balance of multiple choice and short answer questions. On the midterm, on the real midterm, there's going to be graphs that look just like this that you're going to fill in with pictures, just like on the practice midterm. So if you do it ahead of time, that will help you be prepared for the midterm. You really will be at a pretty serious disadvantage if you never tried it and you're not like familiar with the things. Or like there's a bubble sheet. Like you're going to have to fill in, on the bubble sheet, you're going to have to fill in your version number. So stuff like that can save you time if you just look at it ahead of time. Other things like what is on the midterm, like what are the topics? Again, that's answered on midterm 1 info. There's also, like I said, there are many Zoom office hours this week. So the TAs have there's 6 hours of Zoom office hours every day this week for you to go and ask questions. There's Campus Wire, there's the Math Learning Center. You should be coming with questions that you don't understand and let us help you with them. Any questions or comments about the midterm before we start today's class? Okay, so feel free to ask or post on Campus Wire if you have any questions. But we're going to start with the mathematized question on this graph. It looks like I have 85 answers. Who hasn't answered yet? Looks like most people have. Okay, a few people haven't. So put in your guess. If you haven't answered yet, maybe try to do the first one quickly and put in a guess for number 2. I'll give you like 30 seconds because most people have done it. And then we'll go from there. Okay, so I guess something about the sound is not working, but it's beeping for me. It's very faintly beeping. So let's take up this problem. So graph 2 is a little cut off in mathematized, but it's the one directly above graph 1. So how do you go from graph 1 to graph 2? Let's see what you guys said. Graph 1 to graph 2, we're going to start with these blanks. And it's x squared. You do something to it. 94 people said plus, and that makes sense. We are going up. Up is plus. So you plus something. How much do you plus? All you got to do is read the scale of the graph. You plus 3. If you said plus 2, you misread the graph. Look, so 2 is here and the graph is up there. You plus 3. So that is the correct answer. That one is x squared plus 3. So let's go to the notes. Filling in from where we left off last class. Okay. Where do we want to be? Okay, here we are. So here are the graphs. And here is graph 1 is just y equals x squared, the unmessed up graph. And graph 2 is x squared plus 2 on page 214. We go up 2. Except you don't go up 2, you go up 3. That's what I just said. Okay, good. All right. And the 3, we measured it. We took this point and we just measured how big is the distance between those two, and it is 3. So it's always good to pick one point on the graph and kind of use that as your reference to see what's going on. In this case, it makes perfect sense to use the vertex of the graph as the point, and the point moved up 3. Okay, that's graph 2. Not so hard. What about graph 3? That's the real tricky one. Graph 3, x, and this something is in brackets. 25 people chose plus and 76 people chose minus. And the thing that's hard to remember is that even though we're going right, like we started with graph 1 is all the way over here, we're on graph 3, which is all the way over there. So we have moved to the right, right? So on this graph, we're going this way, and that is moving to the right. So it seems like it would be plus 4, but the correct answer is minus 4. So most people got that right. It is minus 4. Minus is correct. Did people say 4? Minus 4. If you said 2, you're probably mixing up the x's and the y's. But it is definitely 4. OK. So it starts with x minus 4 squared. That is doing, x minus 4 squared is doing this movement of moving 4 units to the right. 4 right. OK, the next part is moving it down. This is combining moving right and moving down. The next thing we got to do is go down. Down. Let's do a better green. We got to do 2 down. How do we do 2 down? Well, we do, what did you guys say? Minus and 2. Ooh, OK, some people said 1. If you said 1, it's one box, but a box is 2 units. So watch out for that, right? It's one box, but the box is 2 units. This is another good thing to practice. This will be my last sponsored by the practice midterm for the class. But these graphs, the same exact graphs will be on the midterm. They have boxes that are size 1. Of course, on the real midterm, the questions will be different, but the same graphs. So practice using them and getting used to this idea that a box is 1. In this particular problem today, a box was 2. So down 2. The final answer is x minus 4 squared minus 2. This is to go down 2. So let's reveal the full right answer. Let's reveal and see how people did. So those are the correct answers. And I guess most people, maybe you mixed up. People were good at the lefts and the rights and the minuses and the pluses. Some people mixed up which was which, right? So some people mixed up the 4 with the 2 or misread the chart as 1 instead of 2. But pretty reasonable answers for the most part. Yeah. Yeah, sure. Yeah, so OK, this is a good, let me say this briefly. So the midterm has 3 pages, just like the real midterm and the practice midterm both have 3 pages. The first page is all multiple choice, and they're the questions. The second page is all short answers. You fill in like these little blanks with numbers. And then the third page is the bubble sheet. Yeah. Right, OK, so that's good to know. And that's, again, exactly why I posted the practice midterm. In addition to giving you an opportunity to practice your timing, right? You sit down and take it in 2 hours. If there's a lot of things you don't understand, maybe it's a sign you need to study more. But also practice with the format, right? So 1 page multiple choice, 1 page short answer, 1 page bubble sheet where you put your multiple choice answers. Yeah, great question. All right, any questions about the problem, the mathematize, or the graphs 1, 2, 3? We're about to fill in graphs 4, 5, 6, which are like 1, 2, 3 with a flip. OK, let's finish the graphs. So what's going on in graphs 4, 5, 6? It's the same as graphs 1, 2, 3, except they're upside down. And when they're upside down, this is what I called last class a vertical flip. A vertical flip. We're going to go with that. A vertical flip. And a vertical flip is multiplying by minus outside the function. To be very technically precise, a vertical flip is the same as a flip across the x-axis, or a reflection across the x-axis. I really like to, in my brain, think of them as vertical, spelt definitely wrong, vertical because it helps me remember that it's the y values, right? We're doing a vertical flip that's the y values we're messing with. It is the x-axis, but if you remember that, your brain might flip it around, right, and accidentally have x with vertical and get it mixed up. So I like to remember it as vertical. It's like now it's really bothering me. Vertical. How do you spell vertical? It's somewhere in the notes. Vertical. OK, there. Let's try that. So 4, 5, 6 are all vertical flips. So I can fill in all of them are going to start with minus something, right? Minus something, minus something, minus something, because they're all flipped upside down compared to the original graph. So if you know they're flipped upside down, all you got to do is fill in where they got moved to using what we just did. So that part is the same as graphs 1, 2, 3. The easiest one is graph 4. Graph 4, it literally only got flipped upside down. So graph 4 got flipped upside down and nothing else happened. So everything else we leave the same. Y equals minus x squared, right? Take the original graph, flip it upside down, do nothing else. Graph 5, what is graph 5? Take the original graph, flip it upside down, move it to the left by some number of units. Let's do it in red. Left, how many? Left, how many units is that? That's 5 units. So we're going left 5 units. How do you go left 5 units? Well, you do x something 5 squared, right? Left and right are inside the bracket. Is it minus or plus? This is the one that's backwards to what you would think. This is plus. Okay, x plus 5 squared. Last but not least, in graph 5, you have to account for going up, right? You've got to go up. How many units do you go up? Well, you start here, right? To keep track of where we are. We're starting here and we're going up. It's up 1 box, but 1 box is 2 units. So it's up 2. So plus 2. Plus 2. Let me see if that matches the answer I have here. Yeah, okay, good. So x plus 5 squared plus 2. The plus 5 moves you left. The plus 2 moves you up. Last but not least, graph 6. How do you do graph 6? Graph 6 is all the way over here. And so you gotta, it's flipped upside down. We're gonna move over 3 units to the right, and down 4. So let's do this one a little faster. 3 units to the right and down 4. 3 units to the right, x3. To the right means I put a minus sign, and down 4 units, we said. Down 4 units is minus 4. Okay, so there it is. Okay, maybe I'll leave this one up. I don't know if you want to flip back to the pictures to compare, but those are the answers that I got. Any questions or comments about that one? Okay, so in the rest of the class, we've learned moving around. We've learned how to reflect things, both in the x and the y. The next thing we're going to learn is how to stretch and compress things. So that's the next couple pages of the notes are stretching and compressing. This is what we did last time, the horizontal reflection. So now we're on to a vertical stretch or a compression. Okay, and this one goes the way you would think. You're going to look at something like y equals c f of x, and that is the graph of f stretched when c is bigger than 1. So for example, if you multiply a graph by 2, you take 2 times f of x, you take the whole graph and you stretch it out by a factor of 2. That's if c is bigger than 1, you stretch it out. If c is less than 1, so between 0 and 1, like c equals a half or c equals a third, then you will compress. And that will be compressed by a factor of c. So to show you visually what this looks like, I'm going to open it on Desmos. Let's make a Desmos. And let's start with the graph of y equals x squared. Actually, it occurs to me, okay, we're going to do this mathematize in a second. And I'll copy this out so we have a nice thing to work with. So here is a nice graph, and we're going to see what does it look like to stretch it and compress it. So here is the graph of the function multiplied by some number a, and let's make this a little see-through. So in red is the function multiplied by a, in blue is the original function. It's some crazy looking wonky up and down graph. And right now a is 1. So of course if you multiply it by 1, that does nothing. But what happens if you multiply it by bigger and bigger numbers? Let's see what happens. So it gets stretched out like this. So as you multiply it by a number like 10, it's really, really stretched out. If you multiply it by a number like 2, it's stretched out a little bit. So here it's stretched out by 3.025. And you can see what does stretched out mean? It means if you're positive, you get bigger, more positive. If you're negative, you get more negative. So stretched means sort of away from y equals 0. The positive values get even more positive. The negative values get even more negative, which is exactly what multiplication does, right? So it's not surprising that when you multiply by a number, you're multiplying the y values by that number. This is written in your notes on the next page. So if you go to the next page, there's a little picture. And what we're doing right now is this guy. Stretched graphs are pulled away from the x-axis, and this little cartoon is supposed to represent getting pulled away from the x-axis. The positive numbers get bigger, the negative numbers get more negative. And that happens for positive numbers that are bigger than 1, multiplying by 2 or 3. The reverse is when you compress the graph. So when you compress the graph, it's going to shrink in towards the x-axis, and that happens when c is between 0 and 1. So let's go to the graph, and let's see what happens when it's between 0 and 1. So I'm going to just change on Desmos. Instead of being between 1 and 10, I'm going to say make it between 0 and 1. And let's see what happens. Let's make it animate like this. And we'll hit play. So like it's shrinking down as you multiply by a really tiny number. When you hit 0, you're multiplying by 0. The whole function is 0. And for in-between values, you're somewhere in between 0 and where you started. Right? So we're shrinking the whole graph down, and it looks something like that. OK, so that's the picture in Desmos. I would keep that in your brain. And now we're going to fill in what it looks like on paper. On paper, this is the same graph, but on paper. So this is the paper version of the Desmos, which is not as exciting, but that's what we're using. So the dashed graph is the original graph. And here in exercise 92, we are compressing it by a factor of a half. And to do that, you just multiply by half. So it's 1/2 x squared minus 4. And that will shrink the graph. So it'll get closer to 0 if you multiply the whole thing by a half. What happens when you stretch the graph out? When you stretch the graph out, that is taking everything further away from the x-axis, and that is just multiplying by 2. So 2 times x squared minus 4. So those are the two vertical directions, stretching and shrinking. And you're really taking y equals 0, the x-axis, and you're pulling away from there or pushing in towards there. Questions or comments about that one? So if you're not going to do it around the y-axis, the other option is you can do something else. And that is what this mathematized question is about. So the transformation to f of x will stretch the graph vertically. That's what we just talked about. And now I'm asking you, what do you think the transformation f of 2x will do? It'll blank the graph blank. And your options are, is it going to stretch or compress? I wrote shrink or stretch, but I should have probably written compress. And is it going to be horizontal or vertical? And so I'll let you guys take a stab at that. I think the information for how to join is gone. So hopefully everyone has it. Otherwise, I can try to find the code. But I'll give you guys a minute to put these multiple choice in, and then we'll take it up. Okay, so time is up. Let's see what you guys said. So multiple choice, not too many options. What did people think? 52 to 53, shrink versus stretch. So as close as possible to an exact even split. Is it going to shrink it in towards 0 or stretch it out? And I guess probably this one. Most people correctly got that it's horizontal. So of course, if you're doing stuff to the outside of the function, that's messing with the y values. If you're doing stuff to the inside of the function, that's messing with the x values. It will be horizontal, but will it be a shrink inwards or a stretch outwards? And to show you, I'm going to take the exact same thing that we were doing before. And before we did f of x times a, right? That was the vertical stuff that we just saw. Now we are doing f of x times b, but the b is inside the bracket. So if I turn this on, it should be the exact same function, right? Because right now b is 1. Right? So b is 1, so it's the exact same function. What is going to happen when I press the play button? B will start to cycle through 1, 2, 3. The answer to the mathematized question is what happens at 2, right? So when I play this, it's either going to start shrinking in or it's going to start moving out, and that'll be the right answer. Let's see. Here we go. Whoa. So it goes really fast, and it smooshes in towards 0. The correct answer is that it shrinks. So it shrinks. Shrink is correct. So 50-50 split on the class, it shrinks. How can you remember that it shrinks? I guess it's the same problem as before. When you're messing with the x values, it kind of does the opposite of what you would intuitively expect. So just like adding actually made it go left and subtracting actually made it go right, multiplying by 2 actually shrinks it by a factor of 2. Or compresses it, if you want. And you can see that here, why it's doing that. So that's something to remember. OK, of course, you can have the opposite, right? If b is between 1 and 10, then you are shrinking things down. What happens if b is between 0 and 1? Let's make 0 and 1. And let's see what happens. This will be the reverse. Right? These are tiny numbers b. And what will happen is the whole function will get exploded outwards. Right? The whole function gets flattened to a point. And again, all of the action is happening around x equals 0, around the y-axis. So you can see the value of the function here, that stays the same, right? Right at x equals 0, nothing is changing, and the whole function just gets flattened out around that point. It's like we're zooming in around the function right around here. OK, so let's fill this in on our notes. Let's fill in this idea on the notes. OK, and I'll keep the Desmos like up so you can see what that looks like while I fill in the notes. So, OK, horizontal stretches and compressions. So it's the same thing, but just watch out because it's reversed, right? Cx is stretched for small c. So c is between 0 and 1 is a stretch. And c bigger than 1 is a compression. So watch out for that difference. That's compression when c is bigger than 1. OK, and in the notes, this is drawn like this. And you gotta be careful here because there's a drawing of the y-axis, but it's a horizontal drawing. So if it was me in my notes, I would instead record this like this, right? The y-axis is here, and we're compressing inwards the function horizontally. So a horizontal compress. And over here, we're doing a horizontal stretch. So this is a horizontal stretch. So a horizontal stretch is for small numbers c, and a horizontal compression is when c is big. OK. And the example they do in the notes is, again, the function x squared minus 4. So it's a quadratic equation of parabola that either gets smooshed or is stretched out. So to compress it by a factor of a half, this is the reverse of what you think. You multiply by 2. So it's 2x squared minus 4. So this is f of 2x. Multiplying by 2 actually does a shrinking maneuver. And stretching is the reverse. So if you want to stretch by a factor of 2, you do f of 1/2 x. And so you're going to get 1/2 x squared minus 4. And of course, you can simplify. You can do algebra on it, but that is the core of what we're doing. That's the horizontal stretches and compressions. Any questions about that one? OK, so next up in the notes are 2 examples, just to finish off the section, 2 examples of using all these ideas on some problems we've seen before, calculating them. And OK, I'm gonna turn off the Desmos animation because I can see it animating in the background, and it's driving me slightly crazy. So pause that. And I want to go back to this. OK. So here's an example. It's the function sine of x. And the function sine of x we've done before, it's this function that repeats with a period of 2 pi. So every 2 pi, it does this cycle of going up and down, and then it just does it again and again and again. It has a period of 2 pi. What about the function, which is the same function, but compressed by a factor of a half? And if you compress it by a factor of a half, instead of taking 2 pi to go up and down, now it only takes 1 pi to go up and down, just pi. So take the original function and like a spring, like shrink it down. So that's the function sine of 2x, right? Multiplying by 2 will shrink everything by a factor of a half. And now you might ask the question, what is the period of this function? Well, the period is pi. It's repeating every pi now. Instead of 2 pi, the period got shrunk down to. So that's a periodic function getting shrunk. Compressed in the horizontal direction, I guess, if you want to be fancy about it. OK, what about the next example? Exercise 95, similar kind of question. This time, instead of being about the period of the function, it's about where are the vertical asymptotes. So we have the function f of x equals 1 over x. That's our original function. And we know that the function 1 over x looks like this. The function 1 over x has a vertical asymptote at x equals 0. So this guy has a vertical asymptote at x equals 0. And you can see that from the graph. You can see visually that there's something going on at x equals 0, that vertical line. Or you can see it algebraically by looking at 1 over x. Where is this going to have a problem? It's going to have a problem at x equals 0, where you're doing 1 over a tiny number is going to get bigger and bigger. That's exactly this vertical asymptote idea. Okay, so the original function has a vertical asymptote at x equals 0. The question says, please shift it right by 2 units. How do you shift right by 2 units? You might think it's plus, but it's not. It's minus. 1 over x minus 2. So this will be this function shifted over by 2 units. And one way you can see we've correctly shifted over by 2 units is the vertical asymptote should have moved over by 2. So it used to be at x equals 0, and now the vertical asymptote is at x equals 2. So the vertical asymptote at x equals 2. Okay, and we can see that visually. If you take the graph of the original function and move it over to, the vertical asymptote moves with it. You can also see it algebraically, right? How do you see it algebraically? Where is 1 over x minus 2? Where is that going to have a problem? Well, it's going to have a problem when you try to divide by 0, and that's exactly at x equals 2. So you would, algebraically, you would say solve x minus 2 equals 0, and that gives x equals 2. That is where there's going to potentially be a vertical asymptote. In this case, there really is one. Okay, so we've seen visually how a vertical asymptote moves around. Questions or comments about transformations, this problem or the last problem? This is moving graphs around and that kind of thing. Yeah? If there was a, you're saying what would happen if there was a different minus 2 out here? Like that? 1 over x minus 2, like that? Ah, okay, that's a great question. Let's do this one as a quick little extra question. Let's do new question. This is a good one for the midterm. Draw 1 over x minus 2, okay? What is 1 over x minus 2? Well, the graph of 1 over x is the blue graph. 1 over x minus 2, you're supposed to look at that and recognize by this minus 2 thing that it is a vertical movement downwards. So before the minus 2 was inside the x's, that was a horizontal movement. This one is a vertical movement. So you're supposed to look at this and you're supposed to go, aha, this is down by 2. So we would take the original graph and we would draw it down by 2. Of course, when it goes down by 2, the vertical asymptote doesn't move at all. But now what moves is the horizontal asymptote. So this function, this whole time, had a horizontal asymptote at y equals 0. And we've moved it down by 2, so the new function is going to have a horizontal asymptote at y equals minus 2. And so it's going to look something like this. The vertical asymptote's still at 0. The horizontal asymptote at minus 2. It looks like that. This is the new function. So drawn in red on top of it. It's the original blue function moved down. Of course, yeah, it's starting to, that graph is starting to look quite messy. Here, let me put it on Desmos really quick. So you can get the neat version, which of course we'll never be able to compete with our computer overlords on drawing neat graphs. So okay, 1 over x is the original function. That was in blue in mine. And we talked about 1 over x minus 2, which is the whole thing moved over. I don't remember what color I did that. Maybe purple? And then there was the function 1 over x minus 2 with the minus 2 on the outside in red, which looks like that, as the whole thing shifted down. So those are the three graphs. Maybe that will help you understand what's going on. And again, the way I kind of visualize these, and it might help to zoom out a bit. Well, let me zoom out. Yeah, zoom out. If you zoom out, it'll kind of become more apparent that each of them actually kind of looks like a plus sign. There's sort of a plus sign where the horizontal and the vertical asymptote are, and they kind of hug the two asymptotes. And so you can see it that way. Okay, very good question. Other questions or comments about the transformations in this section? Okay, so that will be it for section 6.10, which means we're done chapter 6. That is the end of the stuff that's on the midterm. So everything else we're doing this week will be on midterm 2, not on midterm 1. But we have reached the end of the midterm 1 material. And here are 2 extra problems if you want to practice. These are good practice for the midterm. But we are now at the end of midterm 1 material. Okay. So for the rest of the class, we're going to start chapter 7, which again, like I said, will be on the midterm of midterm 2, not midterm 1. And that's what we're doing. And chapter 7 is all about some common functions. So chapter 6 was about functions in general, like what happens in general when you add two functions, when you multiply two functions. And now we're being specific. So some specific functions that are common. Specific? That's not right. Okay, some specific functions. I will say it out loud and not write it. Okay, and we're starting with straight lines. So linear equations, y equals mx plus b, that kind of stuff, which you probably know from high school. Straight line equations, linear functions. Y equals mx plus b is literally the first equation we're going to do. So here is a picture of the graphs. I think you guys know what lines look like. They have x-intercepts and y-intercepts. They're either going down or going up, depending if the slope is positive or negative. And here is the first equation form, y equals mx plus b. In the notes, they wrote it as y equals mx plus c. This is like what you've seen before, y equals mx plus b. Over here is a little derivation of y equals mx plus b. Why is it true that if the slope equals m, and the intercept equals c, then y equals mx plus b. That's what the slope form says, slope-intercept form. If you know the slope and you know the intercept, you combine them like this, that gives you the equation of the line. But why is it true? And as usual in mathematics, the but why question is first, but why, and not second. But why? Here is a little derivation of why the equation of the line with slope m and intercept c is y equals mx plus c. And what we do is we look at 2 points on the line. We look at the point xy, which is some generic x and y value, just any point on the line. And we look at the point, the x-intercept, the y-intercept c. And actually c is the height over here. This point, if you were going to label it, is the point 0, c. 0 units across, c units up. And if you calculate the slope between x, y, and 0, c, that's something we did in chapter 4, you get y minus c divided by x minus 0. This is the slope formula from chapter 4. Slope formula from chapter 4. Okay. And if you know that the slope is m, right? I calculated the slope, but you already told me that the slope has to be m. Now I have a beautiful equation. M equals something. M is y minus c divided by x. And if m equals y minus c divided by x, I can rearrange. And if you solve that, move the x to the other side, y equals mx, move the c to the other side, mx plus c, that is exactly the equation. So the reason the equation is y equals mx plus c, you can recover it from the slope formula we learned in chapter 4. Just to show you why it works. And this kind of reasoning, helps you in all sorts of problems, imagining points and calculating their slope and that kind of thing. On the next page, we're going to learn a new formula for lines, and that is called the slope point formula. I sometimes call it the point slope formula. Point slope. In the slope intercept formula, somebody told us the slope and the intercept. In the point slope formula, what did somebody tell us? They told us two things. You're given a slope m and a point x1, y1. So if you're given slope equals m, and you're given the point x1, y1 is on the line, then you have this nice formula, y minus y1 equals m times x minus x1. And this formula is the equation of the line. So it sort of tells you how do you translate from the information you have into the whole equation for the line. And up here, we're going to answer the question, but why? But why is the formula the way it is? And again, it's the same logic as before. We're just going to take some generic point xy, which is some generic point on the line, and we're going to look at the slope to the point we know. So we were given the point x1, y1, and we're going to calculate the slope, right? The slope formula is, again, it's simply y minus y1 divided by x minus x1 using rise over run. So the rise is y minus y1. The run is x minus x1. The slope formula says you divide those, you get the slope. And if you know the slope is y minus y1 over x minus x1, and on the other hand, somebody told me already that the slope is this m, which I drew like an angry seagull over here, m. Let me try this m one more time. Then you have an equation. The slope is m, but the slope is also y minus y1 over x minus x1. So if you set those two things equal and you rearrange, you get the equation that we want. And all you have to do is move x minus x1 to the other side. Y minus y1 equals m times x minus x1. That's the equation we have. And this is a useful formula. I think this one is the most useful one. So slope intercept is easier, but not as useful. This one to me is the most useful one. We're about to do an example. I'm just going to throw some points and slopes at you, and you guys are going to tell me the equation in Math1030. But this is a good place to stop for some questions or comments or anything else about lines. OK, I'll open it up on Math1030 and give you a few minutes. Feel free to put up your hand if you have a question, and we can also come around and help you out. So point slope. This is exercise 96 on page 229. Find the equation of the line with slope 4 passing through the point 3 minus 2. And the way you should input your answer is you're going to input a formula in terms of x. So if you thought the formula was y equals 2x plus 1, you just type in 2x plus 1. Don't type in the y equals that's already there. So I'll give you guys like 2 or 3 minutes to work on that, and then we'll take it up. Again, there's like 30 seconds left. Who is anticipating they will need more time? A couple people. OK. There's only like 3 people, so I'm not going to extend it. So if you're anticipating you need more time, take a guess. OK, 5 seconds left. OK, let's see what people said. Let's take a look. Reveal counts. OK, and Math1030 always takes a minute with these ones, so it's like processing what you guys typed. So, all right, here we go. So again, if you put in a number, probably you didn't try very hard. So it's going to involve x somehow, right? We're looking for something involving x. Maybe you thought you were supposed to enter in the slope, right? The slope is 4. That's true. That was given to you. But we want something involving x. Here is something involving x. 4 times x minus 3 minus 2. Here's an equation also involving x, but also y. This one is actually the same as this one. This thing, if you move the minus 2 to the other side, is the same as this. Y equals 4 times x minus 3 minus 2. And, OK, 29 people answered that. What else did people do? Lots of 4x's with different pluses. This person wrote it as an f. Y equals 4x minus 14. 4x minus 14 is the same as this one, right? If you expand this out, it's minus 12, minus 2, minus 14. So that is actually the same as this answer. This person has a squared. There's no squared. Other things. 3x plus minus 2. 6 people wrote that. OK, I don't know. This one, I think you're mixing up the points and the slopes or something. OK, lots of other answers. What is the correct answer? It's the one that like 30 people had. This one. This is the correct answer. Some people obviously had the right answer but inputted it in incorrectly, which is also fine. Let's go over how you would get this. So this is really using the formula we have. So we're in the notes on this page. Find the equation of the slope. So this is like kind of like a word problem. You have to identify slope 4, so m equals 4. And over here, 3, 2. 3, 2 is the point x1, y1. x1, y1 is 3 minus 2. So x1 equals 3, and y1 equals minus 2. OK? Now we take the formula we had. The formula we had says y minus y1 equals m times x minus x1. Right? In our particular case, this is y minus, what is y1? y1 is minus 2. Minus 2. And m is 4. And x1 is 3. x minus 3. So this is a perfectly valid kind of equation. The y's are mixed up with a 2 on the left-hand side, and the x's are on the right. Question here? Yeah. So you could stop here for a lot of things. And the only thing you had to do for sure in what I just asked you is I said, please express it as y equals something. So to get the mathematize right, you definitely have to do one more step, which is you have to move the 2 to the other side, right? Take this 2, this minus 2, put him on the other side. 4 times x minus 3 minus 2, right? Yeah. Right. Yeah, so I think this is a good question. In a lot of situations, this is perfectly fine. Like what we have is great. And in sort of like in quote real life, you're going to be using the equation to do something. So like getting the equation, nobody cares what the equation is. We actually want to know what is the value of the equation when x equals 20 or something. And then having it like that is perfectly fine. On the midterm, if it says just like get the answer, then you can leave it like that. If someone says, please simplify, then you could simplify it one more, and you could do 4x minus 12 minus 2, which is 4x minus 14. But there is no reason sort of to prefer this over this unless you want less characters, like you want it to be shorter. That's the main reason. And I will say a lot of people kind of make unnecessary mistakes going from here to here. So you should sort of tend to don't simplify unless there's a reason to do it. You might make a mistake. So that was that one. I guess lots of people got it right. But a lot of people didn't get it right. Maybe there were small mistakes here and there. Maybe when you move the negative 2 over, you accidentally did plus 2. I don't know. But is there something I can clear up about the concept? OK, we're going to do one more. That's going to be a harder one. And that is this question about Celsius and Fahrenheit. So the question says, if 0 degrees Celsius equals 32 Fahrenheit and 100 Celsius equals 212 Fahrenheit, find the linear equation to express Celsius as a function of Fahrenheit. So we're converting from Fahrenheit to Celsius. How are we going to do it? The first thing you got to realize is what is x and y. I think this is the first question you're going to ask yourself. What is x? What is y? And the answer is in this last sentence. So we want to express Celsius temperature as a function of Fahrenheit temperature. And to me, that means that the Celsiuses are the y's and the Fahrenheits are the x's, right? Because that way we'll have y in terms of x, y equals something something x. That will be the Celsius in terms of the Fahrenheit. So that's step one. Figure out what are the x's and the y's. The answer, question, answer. y equals Celsius temperature, Celsius, and x equals Fahrenheit temperature, temp. Okay. So you know what the x's and y's are. Now let's take what else is in the problem. And there's actually two pieces of information. There's 0 Celsius equals 32 Fahrenheit. That's one piece. And there's 100 Celsius equals 212 Fahrenheit. Let's do that in red. No, purple. Okay. And these are actually two different points. These are x1, y1s and x2, y2s. So this one is an x1, y1 equals something. And this one is another point, x2, y2 equals something. And what do I mean by this? If you're kind of plotting this visually, we have 2 points. We have x1, y1, that's our first piece of information. We have x2, y2, that's our second piece of information. And we're trying to find the line that goes between them. The line, not the curve, but you get it. So what are what are the numbers? What are x1 and y1? What are x2, y2? 0 Celsius equals 32 Fahrenheit. Well, Celsius are the y's. So 0 is here, and 32 is here. That's the point. 32, x equals 32, and y equals 0 in this one. And in this one over here, same kind of situation, x equals 212 is the Fahrenheit, and y equals 100 is the Celsius. So far, all we've done is we've taken the word problem, we've unpacked it. Now it is a problem where we're given 2 points. Do we have a formula for 2 points to get a line? Well, we never did it in class. We do have a formula with point slope, right? If I had the slope, then I would be happy. I got 2 points, I need the slope. So what I'm going to do is I'm going to calculate the slope. So now I'm going to calculate the slope, calculate the slope. And that's something we did in chapter 4 again, which you should feel free to review. What is the slope? It's y2 minus y1 over x2 minus x1. In our example, y2 is 100, y1 is 0, x2 is 212, x1 is 32. So the slope is this, 100 minus 0 divided by 212 minus 32, also known as 100 divided by 180, also known as 10 over 18, also known as, I guess, another 2 comes out, 5 over 9. Sure. Good. So the slope is 5 over 9. We figured it out using the 2 points. And now we have a slope. We have points. We can use point slope. So what is the equation? The equation of the line, finally, equation is y minus y1 equals m times x minus x1. What is that going to give? Y minus y1 we said was what? y1 is 0. The slope is 5 over 9. M is 5 over 9. What is x1? x1 is 32. So there's our equation. And if you want, you can simplify the minus 0 to get this as the final answer, x minus 32. OK. So there you go. We did one where we were not given the slope. We were given 2 points instead of the slope. And of course, the first thing you do is just calculate the slope and go from there. So if you want, you can put a little package around this problem and call it the 2-point formula, which is earlier in the notes. What is the 2-point form? You calculate the slope, and then you use the point slope. So if you want, you can go fill this in. Otherwise, you can just do it how I did it. Calculate the slope, use the point slope. It's up to you. OK, we're going to stop there. See you guys on Wednesday. Make sure you study for the midterm.